Question, we need to plot the curve first, and it's going to be quite straightforward. Really in these sort of problems we're interested in the x-intercepts much more so than the y-intercepts, for reasons that will become clear. So here, if we want the x-intercepts, you know what you do, you let y equal 0. If you let y equal 0, it turns out that either that must equal 0, what I'm pointing to now, the negative x, or the x plus 1 must equal 0, or the x minus 2 must equal 0. Okay, that's the only way you're going to get y to equal 0. So when negative x equals 0, we can say x equals 0. So that's our first intercept. It's right there at the origin. X plus 1 equals 0 means that x will equal negative 1. There's your other intercept. And x minus 2 equals 0 means that x will equal 2, so there's the intercept at x equals 2. The other thing noteworthy is that this is a cubic, of course, because when we expand it all out, it's going to be negative x times x as the leading term. That's going to be negative x cubed. That means it's going to start off very negative, up that way anyway. When x is negative, y is very positive, and when x is very positive, y is going to be very negative. That's what happens when you get a negative x cubed type expression or equation. Now what the plotting the graph has enabled us to do is realise that we're after the area of two sectors. Area 1 here and area 2. Area 1's above the x-axis, so that's going to be a positive when we integrate over the interval 2 to 0. And area 2 is going to be negative, isn't it? Because it's under the x-axis in the domain x equals 0 to negative 1. So we're going to be careful when we integrate, and what we're going to have to do is find evaluate two definite integrals. So firstly, we need to expand our equation, and that's what I've done here. Firstly, you would expand x plus 1 times x minus 2 to yield that in brackets, and then I've got the negative x out brackets, and then just multiply the negative x by everything inside the brackets. So I'm saying that the area is made up of area 1 plus area 2. So setting up our integration, it looks like this. Area equals, there's your right hand segment, the area 1, with the limits put in, and the absolute value, that's what those straight lines mean. So we're expecting a negative value there, but we ignore the negative and just call it positive over the domain 0 to negative 1 for area 2. So when we integrate for the areas 1 and area 2, the integral is going to remain the same, isn't it? So if you look here, this is on the left hand side, we're dealing with area 1. The integral is the same as for area 2 on the right hand side here, but the only thing that's different, of course, is the limits. Okay, so I hope you can see how we got that integral. The area 1 comes to a nice even 8, area 2 comes to 1/12, and putting it all together we get 8 and 1/12, otherwise known as 97 over 12 units squared. On to question 3b now. What we're doing is we're rotating a shape around the x-axis in this problem. It says the shape formed by the area between y equals the square root of x and y equals x is rotated around the x-axis. What volume has the resulting solid? It certainly helps if you know, broadly speaking, what it is you're rotating. And here's a graph of the situation. The upper curve is a graph of y equals the square root of x, and the lower one is a graph of y equals x. Now you can see that they intersect where x is equal to 1, so it happens that y is also equal to 1, although that's not shown on the axis over here, and they intersect also at the origin. Okay, so that, broadly speaking, is what's happening. So I've got 3 steps you follow in these sort of problems. Firstly, you find the boundaries in terms of x of the origin, set up the integral, subtract the lower function from the higher function, substitute the resulting expression into our template for the volume of a solid of revolution. And finally, we evaluate the integral. So here's our solution. Finding the boundaries, in other words, that point there and that one down there, is quite straightforward in this case. What we do is we let the graph of y equal x equal the graph of y equal the square root of x. In other words, we're interested in where x, the square root of x, equals x. What we can do now is square both sides to get that, and what we're going to do is solve a little quadratic binomial, in this case two terms, by subtracting x from both sides and letting the result equal 0. We factorise in terms of x, and then we have these two equations to solve, which we do via the null factor theorem. So we can see quite clearly that either, for this to be true, either x must equal 0 or x minus 1 must equal 0, in other words x equals 1. Now we're ready to set up the integral. The higher region minus the lower region. Whoops, something's happened here. That's better. What do I mean by that? Well, if we look at our graph again, the region, the higher region is the 1 over our interval of interest, 0 to 1. The higher region is y equals the square root of x, and from that we subtract the lower region, which is y equals x. Okay, so the square root of x minus x is what I'm talking about. Now we substitute that into our template for the volume of a solid of revolution around the x-axis. That's our template there. And as you can see, all I've done is insert the square root of x minus x into our template. Our template's saying that we've got to square the value of y, which is the value of our equation. And remember how to square a perfect square. It's the first term squared, so the square root of x squared is just x minus twice the product. Product means times. That's what these little dots here mean too. Twice the product of the inside term, so minus 2 times x times the square root of x plus the last term squared. So x squared is x squared. We need to tidy that up, making use of our index rules over here. So this is really, square root of x is really x to the power of a half, isn't it? So x to the power of a half times x is x to the power of 1.5, in other words 3 on 2, and then we've got the 2 there. Now we're ready to integrate, and it's the same old story. We increase the index by 1, so x to the power of 1 goes to x to the power of 2, and divide by the new index. That's what that's about. I've got pi out here all the time, of course. Minus 2 times, now 3 on 2 plus 1 is 5 on 2, so, and divide by the new index, and here we go with x squared. The integral of that is quite clearly x cubed on 3. And there are our boundaries. Alright, so substituting, this one's quite straightforward. 1 and 0 are nice to substitute into these integrands. So you should be able to see how we get to that. And with your calculator or otherwise, you should get to pi times 1 on 30. Just a hint here, around this area here, 2 times 1 on 5 divided by 2. Well, when you divide 1 by 5 on 2, you simply tip it over. So it becomes 2 on 5, and 2 times 2 on 5 is 4 on 5. So we would have had 1.5 minus 4 on 5 plus a third, and that comes to 1/30th. Just tidying it up a touch, you know that we always express our answer in terms of cubed units because this is a volume problem, and we leave pi in our answer as well. Okay, that's considered to be an exact form, which is what we prefer. Okay, final part of our practice test is to rotate the shape we came across in the previous part around the y-axis instead of the x-axis. So referring back to our picture of the situation, the shape is the same, but instead of rotating it around the x-axis, around this way, we're rotating it around the y-axis, and the question is the volume going to be the same? Now in general, we would expect not, but let's have a look in this case. Okay, well, don't forget that the idea here is that we start off with a template like this. Now this is for the one we use for the rotating around the x-axis, but for the y-axis we've a few things need to change. Okay, so instead of that template, what we do is we, instead of the y squared, we put in an x squared. So the volume, this is for rotate. This second one's for rotating around the y-axis. Oops, that's not very neat, is it? So when we're rotating around the y-axis, things are a little bit different. We make x the subject of each of our equations. So remember we started off with the two curves, y equals the square root of x, and the other one was y equals x. So making x the subject of our equations, what we can do here is square both sides and reverse the order. So squaring the square root of x, we get x, and that equals y squared. Here we don't have to do anything at all except perhaps write it in reverse order. Okay, so we're going to, there are two equations now, and all you need to do is substitute, well, find the higher area, and from that subtract the higher region, and from that subtract the lower region, and substitute into our template around here. Okay, so let's do that now. Our higher region, if you look at the graph, here it is, we're rotating around the x-axis, so it's in fact this region. That's going to be the high region, the y equals x, or x equals y, and from that we're going to subtract this other one. Okay, so here we go. Let's set up our integral. So the volume is going to equal pi. Oh, by the way, our limits didn't change. If you look at the graph, if you look back at the graph, our limits didn't change. Ordinarily they will, and you've got to be prepared for that. But anyway, here the higher region was y, x equals y, and we're going to subtract the lower region, so y squared. And don't forget, we square all of that, and we are going to integrate in respect of y. Again, expanding our perfect square, we get the first term squared is y squared minus twice the product, so minus 2 times the product of y and y squared, which is y cubed, and plus the last term squared. Y squared times y squared is clearly y to the power of 4. Now we're ready to integrate. And when we integrate, it's the same old story, isn't it? We integrate term by term, and we increase the index by 1 and divide by the new index. So y squared goes to y cubed on 3. Here it's going to be 2y to the power of 4 on 4. Now I realise that can be simplified to just y to the power of 4 on 2, but I'm leaving it there so you can see where everything comes from. And this one's simply y to the power of 5 on 5. Now what we need to do is substitute our boundaries in. This one's going to be easy, isn't it? So that's what it comes down to, and then you should find that the volume is equal to pi times 1 on 30 units cubed. I'm not going to put the units cubed in just yet, but volume is equal to pi on 30 units cubed, which equals the answer we had in part 3b. So in answer to our question, the volume is the same. Okay, now the advanced students might want to ponder why that is the case, because generally you'll find that when you rotate a shape around the x-axis, you'll get a different volume to when you rotate it around the y-axis. Okay, but I'll let you sort that out for yourselves. Bye-bye.